This is back titration sample number 4. Welcome and stay on until the end of the video. So we are provided with solution A, which is hydrochloric acid of a known concentration. We also have solution B, which we are told contains 10 grams per liter of our alkali, sodium hydroxide. And finally, we are given 1 grams of an impure carbonate as solid C. So in this experiment, we are required to determine the concentration of solution A in number of moles per liter in our procedure number 1, and then later on in procedure 2, we shall be required to determine the percentage purity of our solid C, the carbonate. For procedure 1, we are told to fill a burette with our alkali, that is solution B. Then we are also told to pipette 25 cubic centimeter of hydrochloric acid, solution A, into a conical flask. We are then told to add 2 to 3 drops of screened methyl orange indicator and titrate. We are supposed to record our results in the table below and repeat the titration 2 more times to complete table 1. At this point, we always advise our students to have their own summary of the solutions given so that they are able to easily refer to the solutions during calculations. So, solution B here, we are told, is sodium hydroxide that contains 10 grams per liter of the same. And then we are using 25 cubic centimeters of hydrochloric acid solution A, but this acid, the concentration is unknown. With that, we go to fill the table, and because this is like a dry practical where we are supposed to have a discussion of the same and not doing the practical together, we will fill the table assuming that we did the practical. So for titration 1, let's suppose a student started at an initial burette reading of 0.0 cubic centimeters, and then we were able to obtain a final volume of 22.1 cubic centimeters. That gives volume of B used as 22.1. For titration 2, because we did not want to waste time, our initial was the final for titration 1. When we were through with the titration, the final burette reading was 44.0. If we do the subtraction, we get volume of B used as 21.9 cubic centimeters. For titration number 3, we were able to fill up our burette again to 0.0, and after we were through, we were able to get a volume of 21.7. That gives volume of B used as 21.7. We have always advised our students to have such kind of volumes. These volumes ensure that the first 2 values form set 1 of figures or of volumes that can be averaged, and the second and third also form set 2 of values that can be averaged. It's always intelligent to do this, and there is a video that we did with an intent to just explain why it is prudent for a candidate to have two sets of volumes that can be averaged anytime we are doing a practical. With that, a candidate should now use any of the two sets to do the average volume. First question, we are asked to calculate the average volume of solution B used. And for our case, we shall pick the first two values, that is 22.1 added to 21.9, and then we shall divide by 2. That gives a volume of 22.0 cubic centimeters. We proceed to question B, where we are asked to determine the concentration of solution B in moles per liter. Going back to our information, solution B was simply sodium hydroxide, and the information we had was that it was made by dissolving 10 grams per liter of the same. So to answer this question, we need to start by calculating the relative formula mass of our alkali. Sodium has been given as 23, oxygen is 16, and hydrogen is 1. That gives RFM of 40. So the interpretation of this is that if we have 40 grams per liter of our solution, we would end up having a 1 molar solution. But for our case, we only had 10 grams per liter. So using first principle approach, we then argue out that how many moles would we then have. Cross multiplication gives 10 multiplied by 1 divided by 40. And we end up having a 0.25 molar solution. Doing this, we have answered our question. We then proceed to the rest of the questions. So for part 2, we are now asked to calculate number of moles of B used. Molarity of B, we have just calculated as 0.25 molar solution. And during our titration, we were able to get average volume of B used as 22.0 cubic centimeters. With this information, we can now go ahead and get the number of moles of solution B, which was sodium hydroxide, that was used. So the argument is, if in a liter we have 0.25 molar solution, how many moles would we then have in 25 cubic centimeter? Cross multiplication gives 25 times 0.25 divided by 1000, and we get an answer of 0.0055 moles of solution B that were used. To the next question, we are asked number of moles of solution A that were used. Solution A is our hydrochloric acid, and not much information is given here apart from the volume that we pipetted as 25. The other information is not given. For this purpose, before we answer this question, we are supposed to obtain mole ratio from the reaction that took place during our titration. So during our titration, hydrochloric acid was able to react with sodium hydroxide to form sodium chloride and water. From here, the equation is balanced, and we can see that mole ratio is 1:1. So it therefore means if we used 0.0055 moles of sodium hydroxide, then we also used the same number of moles for solution A, and that would be 0.0055 moles. Before moving to procedure 2, we were asked to calculate the concentration of our hydrochloric acid in moles per liter. So this number of moles that we have just calculated here were present in 25 cubic centimeter. So to get moles per liter, our argument would be so easy that if 25 cubic centimeters is able to contain 0.0055 moles, how about a liter of solution? Cross multiplication gives 1000 times 0.0055 divided by 25. And we obtain a 0.22 molar hydrochloric acid solution A. With that, we proceed now to procedure 2. In procedure 2, we are told to use a measuring cylinder to measure 100 cubic centimeter of solution A. Solution A, we have just found to be a 0.22 molar hydrochloric acid. This summary is very important for a candidate who wants to really have an easy time with the calculations. So we will do that into a beaker. Then we add all solid C, which was a 1 gram. Solid C is 1 gram of an impure carbonate. So we would start the mixture and allow to proceed for about 5 minutes. This is to ensure that all the carbonate has been used up, but we shall have some excess acid that we shall now titrate a second time against our alkali. So we are told to label the solution obtained as solution E. This is simply excess hydrochloric acid that will not have reacted with our carbonate. We are told to continue to fill a burette with our sodium hydroxide solution B, which was a 0.25 molar solution from our procedure 1. So we then pipette 25 of E into a conical flask, add 2 to 3 drops of screened methyl orange indicator and titrate. At the end of the day, we are supposed to fill table 2. So again, let's assume a candidate got 0.0 as the initial burette reading. After titration 1, we were able to read 8.9, giving volume of B used as 8.9 cubic centimeters. Because the volume used was very minimal, we can afford to begin the second titration from where we stopped the first. Let's assume we got a final volume of 18.0. That gives 9.1 as the volume used. Again, we still have some solution B in our burette. So even for experiment 3, we can afford to proceed from where we stopped experiment 2. So we start at 18 and we end at 26.7, giving us a volume of 8.7. Again, these are 2 sets of values that can be averaged, but for our calculations, let us use the first 2. So average volume of B used, we should go for 8.9 and 9.1 over 2. That gives 9.0 cubic centimeters as the average volume of B used. To the other questions, we are told to calculate moles of hydrochloric acid in 25 of solution E. So here, these moles of hydrochloric acid, we are not able to tell until we write an equation for the reaction that took place during our second titration. We actually reacted solution E, which is excess hydrochloric acid, with our alkali. So we are able to form sodium chloride and water. Again, the equation balances out. We see mole ratio is 1:1. So if we know moles of sodium hydroxide that reacted, we can know moles of hydrochloric acid. So let's start with the moles of sodium hydroxide that reacted. Sodium hydroxide, from the information we have up here, it was a 0.25 molar solution. But we only used 9 cubic centimeters of the same. With that information is enough to give us moles of it that reacted. So we shall have the argument that if a liter contains 0.25 moles, what about 9 cubic centimeters that we used during our titration? This would give 9 multiplied by 0.25 divided by 1000, and we get 0.00225 moles. And because mole ratio is 1:1, it therefore means that moles of hydrochloric acid in 25 cubic centimeter of solution E remains 0.00225 moles. The argument is because mole ratio is 1:1. Next question. Moles of hydrochloric acid now in 100. These moles are present in 25. What about 100? So if 25 cubic centimeters of solution E contains 0.00225 moles, how much or how many moles would we have in 100 cubic centimeter? This is 100 by 0.00225 divided by 25, and we get 0.009 moles. So after our hydrochloric acid had reacted with the carbonate, these are the moles that remained. But originally we picked 100 cubic centimeter of our solution A. Solution A was a 0.22 molar hydrochloric acid. So armed with these two pieces of information, we can easily tell now the number of moles of hydrochloric acid that reacted with the carbonate. We proceed to that section in a moment. In part 3, we are asked to calculate moles of hydrochloric acid in 100 cubic centimeter of the original hydrochloric acid solution A. So you remember, this was a 0.22 molar hydrochloric acid. From it, we picked 100 cubic centimeter. So to get the answer here, we shall argue out that if 1000 cubic centimeter is a 0.22 molar solution, how many moles then would we have in 100 cubic centimeter of the same? So this would be 100 multiplied by 0.22 divided by 1000, and that gives 0.022 moles of hydrochloric acid. To the next question, we are asked to calculate moles of hydrochloric acid that were used up in the reaction with solid C. So originally, moles of hydrochloric acid in 100 cubic centimeter of solution A were 0.022. Moles of hydrochloric acid in 100 cubic centimeter of solution E, which actually took part in the second titration, were only 0.009 moles. So getting the difference, we are able to get moles of HCl that reacted with our solid. And this gives 0.013 moles. Easy to understand if you follow the meaning of back titration. Part 5, we are told to calculate moles of carbonate solid C that reacted with hydrochloric acid if the ratio between carbonate and acid is 1:2. So here we shall simply divide the answer in part 4 above by 2, and we get 0.00065 moles. To the next question, we are told that given that the relative formula mass of the carbonate is 106, we are then supposed to calculate the mass that reacted. So here, 1 mole of the carbonate is 106 grams. That is the interpretation of relative formula mass. So we would then ask, if 1 mole is 106 grams, what about 0.0065 moles that took part in the reaction? This would be 0.0065 times 106 divided by 1, and we get 0.689 grams. Finally, we are asked the percentage purity of the carbonate. The carbonate, pure carbonate, was 0.689 grams. Actually, what took part in the reaction? Originally, we were provided with 1 gram of an impure carbonate, so then we multiply by 100 to get percentage purity. This gives us 68.9% pure carbonate. Thanks for keeping it here till the end of this video.